In this video, I will present you our result for estimating the mean of a multivariate distributions using a quantum computer. This is based on joint work with Arjan, Cornelissen and Sofiene Jerbi. The statement of the mean estimation problem is the following one. We have a random variable x defined over some probability space, taking value in a d-dimensional space defined over the reals. The parameter d, which is important for our case, is the dimension, and it will be larger than 1. The most important property for the mean estimation problem are the expectation of the random variable denoted by mu. And we will also use the covariance matrix denoted by sigma, and in particular the diagonal of this matrix, which encodes the variance of the d marginal distribution corresponding to each of the d coordinates of x. The goal of the mean estimation problem is to produce as output a vector of dimension d, which is a good approximation of the mean mu. For that, we will need the standard assumption that the trace of the covariance matrix, which is just the sum of the variance of the marginals, is finite. This problem, which is very general, has many applications, for instance, in statistics or in the Monte Carlo method. But in this talk, we will consider just the most general setting, and we will work with an abstract model that can be applied to all of those applications. So let me give you the input model that we will be considering. So this is a reminder of the setup we have. And first, classically, the usual access model used to study the mean estimation problem consists of obtaining outcome from the input probability distribution and evaluating those outcomes according to the random variable x, and then observing the value of x omega. So the standard measure of complexity in this case is called the sample complexity. And this is the number of times you can use those two steps. And the goal is to use n classical samples to produce the best possible estimate of the mean mu. So now in the quantum setting, we will quantize this input model in the following way, which is quite standard in the literature. So first, we will replace this outcome with what we call a distribution oracle, which is just a unitary operator with the following property. If you apply it on the all zero base state, it will produce as output a quantum state, which is a superposition over the element of the sample space, with the amplitude encoding the probability distribution. So in particular, if you measure this state in the basis defined by the elements omega, what you will obtain is exactly the same thing as if you use the classical input model, the first step of the classical input model. The second part of the quantum access model is to have a second oracle, which will provide us a way of evaluating the random variable in superposition over the element of the sample space. So it is quite easy to observe that this model, the quantum model, is at least as powerful as the classical model, because you can simulate a classical access by using those two unitary operators. But it can be more powerful because those two operators we can also perform more complicated operations than just preparing those states. So as a simple observation, and by definition of our problem, observe that this element, x omega, in practice, it is a vector of dimension d, meaning it is a tensor product of d basis state, each of which encode a different coordinate of the input random variable. So now the complexity parameter in the quantum access model which is the generalization of the classical sample complexity, will be the number of times we can apply each of those two oracles in our algorithm. We will also call that samples or quantum samples sometimes. And the goal will be to understand if we can use n times those oracles, what is the best possible estimate we can produce to approximate U. So now let me give you the result. And to be a bit more precise, this is the kind of guarantee that we will try to achieve. Our goal is to produce an estimator of mu tilde, such that if you look at the distance between mu and mu tilde according to the Euclidean norm, then we want this distance to be at most epsilon n, where n is the sample complexity parameter, with probability at least 2/3. And the goal is to minimize this quantity epsilon n when n is fixed. So let's see what is the best possible epsilon n we can achieve. And first, if you just have classical access to the input, this is the optimal error that you can achieve. Dimension 1 is going to depend on the variance and the sample complexity. And in higher dimension, it will depend on the trace of the covariance matrix. So the way you can obtain those results is quite easy. You can just compute the empirical mean, which is the average of n classical samples. And this is optimal. Now, if you get access to quantum oracles, in dimension 1, it has been shown in the last few years that you can obtain something which is better than what you can do classically. Instead of having a square root dependence on n, you can have something which is a linear dependence on the sample complexity. And this is again optimal up to logarithmic factor. And now the contribution of our work is to consider the case of higher dimension. And what we show is the following thing, which is a bit more complicated than the statement of the previous result, because there are two different regimes which are displayed on this picture. The first regime is the case where n, the sample complexity parameter, is smaller than the dimension. And in this regime, we show that it is impossible to obtain any advantage by using the quantum access model. So the best you can do in this regime is just to apply the classical algorithm. The second regime is when n is larger than b. And in this case, we were able to obtain a new algorithm that achieved a quantum speedup compared to the classical setting. And more precisely, we show that the best possible error is going to be the square root of the dimension times the trace of the covariance matrix divided by n. So it generalizes the case of dimension 1 to an arbitrary dimension. So in our result, there are both lower bounds and upper bounds. But for the rest of this talk, I would like to focus on this particular result and proving the upper bound, meaning I will try to give you a description of the algorithm in the regime where it is possible to obtain a quantum advantage. So let me begin by describing the outline of the algorithm. And as you will see, there are three steps in the algorithm. So the very first step, which is very simple, consists of getting a crude estimate denoted by mu bar, which will be at distance about the square root of the trace of the covariance matrix. So this estimate will be very simple to compute. You can just take the average of a constant number of classical samples. You don't even need to use the quantum model. The second step, which will be a bit more interesting, is to get an idea of the spread of the distribution around the mean. So for that, the first thing we'll try to do is to find the radius A1 of a ball that contains about half of the total mass of the input distribution. Then we'll try to find the radius A2 of a second ball that contains about 3/4 of the input distribution, centered around the crude estimate. And we'll continue like that until we arrive at the last ball, which will be the larger ball, and that will contain about 1 minus 1 over n squared of the total mass of the input distribution. So in a more mathematical way, what those values are, they are the quantiles, AL, that satisfy the following property, which says that the probability of sampling a value which is outside the ball of radius AL, centered around nu bar, must be about 1 over 2 to the L. There is an exponential decrease in the parameter L. And this parameter L is going to be between 1 and 2 times log n to arrive at the last ball. So I will explain you in the next slide how we can estimate those quantiles value efficiently. But for that, we will need to use the power of the quantum model. The third and last step of the algorithm will consist of estimating the expectation of x in the following way. We will consider separately each of the areas defined by 2 consecutive quantiles value. So the first area will be the inner circle, the red part, the red ball. The second area will be the first ring defined by A1 and A2, etc., until we arrive at the last ring. And for each of those areas, we will estimate the expectation of x truncated according to this area. And then we just take a summation over all those estimates, and this will be our final estimate for the expectation of x. So you may notice that we will not try to estimate the expectation outside the larger ball. And the reason for that is because we can show that outside this larger ball, the contribution to the expectation of x is going to be negligible. We can just discard this part of the distribution. So I will explain you how we can estimate each of those truncated expectations. And again, it will require using the quantum input model. So let me now first explain how we estimate the quantiles. So what we are interested in is this new random variable y, which is the distance between x and the crude estimate in L2 norm. And this is the value we try to estimate, the quantile of order AL. So let's imagine this is the distribution of y. And let's begin with the first quantile value, A1, which by definition must be close to the median of the distribution of y. So for estimating A1, it's pretty simple. We can just compute the sample median, which will require a constant number of samples. Actually, we just need classical sample for A1. So it will be somewhere here. And then for estimating the next quantile value, A2, which must be at about 3/4 of the distribution, we can do it in the following way. We can consider the renormalized distribution of y, conditioned on being larger than A1. And the median of this new renormalized distribution will be close to A2. So again, it means that A2 can be obtained by taking a constant number of samples from the conditional distribution obtained by renormalizing the random variable y. And then can continue like that. So A3 can be obtained as the median of the distribution conditioned on being larger than A2, etc. So it gives us the following algorithm, which is for estimating AL, what we can do is just take a constant number of samples from the renormalized distribution. So the difficulty in doing that is that this renormalization depends on an event which is less and less likely to happen when L increases. And in particular, the probability of this event for an arbitrary value of L is about 1 over 2 to the L by definition of the quantiles value. So now, if you just take classical sample, the probability of observing this event is about 1 over 2 to the L. So you will need 2 to the L classical sample before you can obtain one value from this conditional distribution. Instead of doing that, we will use the power of the quantum model to do it faster than classically. And more precisely, what we will do is we will use amplitude amplification, which is a generalization of Grover search, and which gives us a way of boosting the probability of an event quadratically faster than what it is possible to do classically. And in particular, in our case, by using amplitude amplification, we will be able to obtain such a sample in times square root of 2 to the L minus 1. So the total complexity, when we arrive at the very last quantile value, will be on the order of n, because the probability of the last event is about 1 over n squared. So this is the right order of magnitude. And this has to be multiplied with the total number of steps, which is logarithmic by definition of how many quantiles we are considering. So this is it for the description of the estimation of the quantiles value. And now let me move to the last step of the algorithm, which is estimating the expectation restricted on each of the rings defined according to the quantiles we just computed. So let's focus on a particular ring, because it will be the same operation applied on each ring separately. So again, a ring is defined as being an area of the ball between radius AL minus 1 and radius AL. So let's define XL to be the random variable obtained by truncating the value outside this ring. So use the indicator function, which is 0 outside the ring. And we subtract the crude estimate U bar to center the distribution. So the first step is going to be very similar to what we did in the previous slide to estimate the quantile. And again, this step will consist of using amplitude amplification to boost the probability of observing an element that is inside this ring. And again, because the probability of observing something inside the blue area is 1 over 2 to the L, the cost of boosting this event will be the square root of 2 to the L. Now, for the rest of the algorithm, we will need to introduce a grid of points defined in the following way. So this grid is defined over a d-dimensional space. It is an hypercube in dimension d. And the point in this grid, denoted by u, they are at a distance at most 1 over AL to the center, according to the L infinity distance. So in particular, the radius of this hypercube is going to decrease when the radius of the ball we are considering is increasing. And the reason for which we decrease the radius of the hypercube is because of the following property, which is one of the most important properties of our algorithm, and which says that if you take the inner product between a point of this hypercube and the random variable, then with high probability over the choice of u, the inner product is going to be at most 1, which is much smaller than the naive upper bound of square root t, which you will obtain if you just apply a Cauchy-Schwarz inequality. And now the reason for which this property is interesting is because since it is at most 1, we can encode this value as the amplitude of a quantum state without having to renormalize it. And we use this property to construct something which is called a phase oracle. And more precisely, so I won't go into too much detail, but what we can obtain is a unitary operator that will map each point of the grid to the same point, but with a phase that encodes the inner product between U and the expectation of XL. And this phase encoding can be implemented in a very efficient way because it will require a constant number of calls to the subroutine constructed at the first step. So now observe that what we have is a phase encoding of a linear function, which is the inner product function. And the gradient of this linear function is the expectation that we try to estimate. So now we can use this property to apply the Bernstein-Vazirani algorithm, or more precisely a generalization of it defined over the real numbers. And this algorithm, which basically consists of using the quantum Fourier transform, will use this phase oracle to construct an estimate of the gradient with the following error guarantee in L-infinity distance by using both number of calls to the phase oracle constructed at the second step. So what is important to observe is that there is a trade-off between two different things. The first one is the number of steps we perform at the first step for the amplification. And the second part of the trade-off is the number of steps performed by the gradient estimation at the third step. And you can see that when the radius of the ball is increasing, the amplification is going to take a larger amount of time because we need to amplify a smaller event. But on the other hand, because the contribution to the expectation is becoming smaller and smaller, we can spend a smaller amount of time at the third step on the estimation. And this trade-off is the reason for which we are considering those different rings and splitting the estimation into each of those rings. So the next observation is about the error term, is about the error guarantee that we are achieving here. And by a simple calculation, one can show that this quantity is going to be at most the square root of the trace of the covariance matrix divided by n. This is by property of the quantiles that we chose. So now we just have to switch from L-infinity distance to L2 distance. And for that, we just apply Hölder's inequality, which tells us that indeed the error that we achieve is of the order of the square root of the dimension times the trace divided by n, which is the result that we wanted to obtain. And this concludes the description of the algorithm. Now let me conclude. So this is first a reminder of the main result that we obtained in our work. I would like to give a few open questions. So first, it would be interesting to understand exactly what is the optimal dependence on the failure probability, denoted usually by delta. So here, for simplicity, I took delta to be a constant, 1/3. But if delta is a parameter of the problem, it would be interesting to understand exactly what is the dependence on delta. So this is the best possible complexity classically in terms of delta. And quantumly, we don't know exactly what it is. The second open question is to understand the mean estimation problem with respect to other norms than just the L2 norm. And then we can also consider other kind of access models. So for instance, instead of having an evaluation oracle, we could have something that encodes the random variable inside the phase directly. And finally, a last open question is to understand whether having some extra knowledge about the covariance matrix may help to improve the error parameter. With that, I thank you for your attention. This is the end of this talk.